All right, please go ahead. Our next speaker is John Klauder.
Are we ready?
I think we are. We see like a color bar down at the bottom of the screen.
Yes, that's okay.
Okay. Yes, please begin.
Okay. This is a short review of canonical quantization, a short review of affine quantization. Validity requires special phase-based metrics and proof that affine quantization can solve what canonical quantization cannot do. Two formulations of quantum field models and two formations of quantum gravity. Some basic facts before we start. Here's a simple truth. For variables or for functions, if A times B equals C and A equals C divided by B, if two are known, the third should be known. But if B and C equals 0, what is A? If B and C is infinity, what is A? To be safe, accept magnitude B and magnitude C pointing to magnitude A, all between 0 and infinity. Now that's good mathematics, but maybe physics has something to say. Here is mv equals p, that's mass times velocity equals momentum. If the velocity is 0, then the momentum is certainly 0, and that's fair enough. But if m equals 0 and v equals 6 and p has to equal 0, that's not fair. So we're going to omit the point 0 of m. Now here's a field of nature, and here's its time derivative when that happens, and the product is over here. This should not be taken to be 0 because it's the pi. Pi, it should be the 0 for the kappa. And pi, again, we will take it take those away from us. So we now draw attention to these ABC terms. Now here's the second one. Here's a model which is classical, okay, but it's certainly not quantum. Here is the Hamiltonian for the harmonic oscillator, classical, p squared plus q squared over 2. And using canonical quantization, we promoted to cap p squared and cap q squared. And that's all familiar to most of you, I'm sure. But we're going to change the coordinates. Q becoming q bar cubed, p becoming p bar divided by 3 q bars squares. Well, the Poisson bracket of QP is well done for these story. And we now have the Poisson bracket for Q bar and P bar. Well, we can put that into our Hamilton function here. And this is a bit okay. But when Q goes to 0, that's a little tricky. And this has to be organized to go back to the point P that you want. Well, that's already an ABC problem. But now let's promote this canonical quantization to operators. That's P stag over 9 Q to the 4th, Q to the 6th. Well, good heavens, that's certainly not anything having to do with the harmonic oscillator. And indeed, the signal that this is bad physics is that Q equals 0 because P has its own dependence. So let's go beyond that now. Let's get down to business. Here is a canonical quantization. And in this region of the screen, we're going to put down the purpose of the slide. And here, this is a tool. Now, we have P and Q between plus and minus infinity, the Poisson bracket to be 1. P can be promoted to a self-adjoint operator. Q can be promoted to a self-adjoint operator. Here's the computation relation. And finally, here is our coherent state labeled by little p and little q. Exponential of minus I little q capital P over h bar. Exponential of little I little p capital Q over h bar, and a fiducial vector here, which is normalized. Now, Dirac has said that the classical function of the classical variables can be made into the quantum function of the classical variables, but that requires Cartesian coordinates in order to obtain physically correct quantizations. Let's see what we can do. Here is an expectation value in our fiducial vector. It has only a C on this side, so that means that the Q and the P expectations are both 0. And now Q squared plus P squared should be in a function depending on H bar. Now here is the quantum Hamiltonian of the quantum variables in an expectation value in the coherent state. That leaves us to a semi-classical function on this side because there's H bar that could be here. And now we unravel the Unitarian for there to have an expectation of the fiducial vector of capital P plus little p and capital Q plus little q. Now, suppose we have a general polynomial here, and there's going to be only one term in which P and Q are alone, and that's this picture down here. The rest involves H bar and other terms as well. But now if H bar goes to 0, that goes away. This never had 0, and any H bar here has disappeared. So we have now the possibility of doing this exactly. All we need are the Cartesian coordinates. Well, let's take our coherent state and take a differential. Aha, but just now pause in a minute. Suppose there was a phase factor here, e to the I phi, e to the I f of little p and little q. Well, that would get knocked out here and here, so that has no physics. But this is a special metric story, a Fubini-Studi metric from long ago, in which the phase factor contribution, which would be here and here, is canceled there. And therefore, there's no longer any relation about that. And what's left over is omega to the minus 1 dp squared plus omega times dq squared, which is indeed Cartesian, exactly what we wanted. And I want to give a bravo to the coherent states here, which have been heavily used in this way. We're going to call that flat surface now something else, a constant 0 curvature. Now, here is the affine quantization story. We're going to start with P times Q, the same as before, those P's and Q's, and equal that D. But we want to make D and little q the new basic variables. Well, here's an ABC story already. P is the time derivative for Q, and that needs to be 0 for this 0. So we have Q, which will take 0 away from the situation. Now that leaves us with Q negative and Q positive. We throw away the negative and we accept and keep the Q positive. It's useful that Q is going to be dimensionless to make future equations easier. Here's our Q and capital Q 0. Here's our little d being promoted to capital D, which is P dagger times Q plus QP over 2. So this is self-adjoint. Indeed, although capital P dagger is not equal to P because we have made Q greater than 0, for computational purposes, P dagger Q equals PQ, namely it's finding the place at the point where we have cut out our say surface. Now, here is the commutation relation here. And this is like a Lie algebra. And the Lie algebra of the affine group gave us the name for our procedures. Now here is the new coherent state, P semicolon Q, exponential of little I, little p, capital Q over H bar, and exponential of minus I, natural logarithm of little q times capital D over H bar. And here is a fiducial vector, which is normalized. Now we have a different story for the expectation values here. We have a little a over here, which means capital Q expectation value is 1. D is still 0. And deviations from capital Q equal to 1 have a function of H bar. Now here is a new function, which we'll call H prime, because it's not actually the Hamiltonian function. I may slip sometimes and say Hamiltonian, but don't worry. This is just a quantum function of the quantum variables of the affine quantum variables in the affine coherent states. This is still, again, a semi-classical story unraveling these unitary operators. We find this is a function of capital D plus B times P times Q times capital Q and little q times capital Q. Not average, not adding like it was for the canonical, but now multiplying. Indeed, little p times little q could be a factor on capital Q. It could make it large, could make it strong. And I'm going to give it a name as the dilation variable, because that can dilate things it sees. And this is the dilation operator then. Once again, in the general polynomials, there's only going to be one term, which is full for the terms over here, and that's over here. So this is the quantum function of these variables. And here's the rest of that story. But if H bar went to 0, this would go to 0. This never had a 0, and any 0 here was gone. Now, this is kind of like what Dirac has predicted, and we'll see if we have a Cartesian metric. Well, here is the Fubini-Studi metric for this problem. And lo and behold, it is quite different. It has a constant to the -1, q squared times dp squared, plus that constant times q to the -2 dq squared. Hardly Cartesian. However, it is a fantastic space itself. It's called a constant negative curvature in a magnitude of -2 over beta h. You've heard of perhaps constant positive curvature, just like a tennis ball or a Brachton ball. A basketball. Anyway, we want to give it a bravo to this particular slide. Now, here's the short list of valid quantization rules. P and Q between plus and minus infinity. Metric, they should be Cartesian as variable. This is not exactly, of course, part of the phase space plane. The H bar was necessary to be positive to have this happen. But nevertheless, that makes the classical function of the classical variables equal to the quantum function of the classical variables, which are then promoted to that quantum function of the quantum variables. That's for canonical quantization. Now for affine quantization, we have P between plus and minus infinity still, but Q must be strictly positive. Our metric here is a constant negative curvature, a constant times Q squared dP squared, constant to the inverse, Q to the minus 2 dQ squared. And I have an arrow here I want to remind you that this has something important to say in the future. Okay, these are the continuity stories. Here's a function here for these variables, is the quantum function for these variables and the quantum function of the quantum operators. Now here is an example. This is called a half harmonic oscillator, in which capital Q and little q, of course, are greater than 0. That makes P dagger not equal to P, and there's many possibilities of promoting little p squared plus little q squared into a full harmonic oscillator situation here. Here is the situation now is P dagger is different from capital P here. And we're going to introduce 2 new variables, R and S, both running over the whole real line. And we choose to set Q equal to S squared. Well, that helps the positivity situation, certainly. We have a Poisson bracket of Q and P equal to 1, which was, of course, necessary for the quantization before. And if we let P equal R divide by 2S, then we have a Poisson bracket for the S and R pair. That means we can promote them to quantum operators with the regular canonical quantization rules. And here we have our operator promoted. It's R, S to the minus 2, capital R again, plus S to the 4 over 2. Well, remind yourself that we just did the Q equal to the Q bar to the cube, and that's quantum story was not good. I'm telling you again that this is not so good either, because S, capital S, is going to be 0, and that's infinity, and that's not part of the story here. So, but this is an attempt by canonical quantization to deal with the half harmonic oscillator. Now let's see what affine quantization can do. First, we're going to look here. We have our P squared over plus Q squared. Well, that's D squared also over Q squared, divide by Q squared. And here's the promotion to the quantum operator's function, capital D, Q to the minus D, capital Q plus Q squared all over Q, Q being positive, and our space is strictly positive. Now, a capital D is made up of capital P and capital Q, and we can unravel those from here and get this point down here. Capital P squared, 3/4 times H bar squared divided, we would get that divided by capital Q squared, and Q squared over all over 2. Well, this has brought the situation into a canonical quantization. And in fact, we will call that an affine quantization, moving into the classical quantization and including H bar terms by itself. This problem has perhaps some idea, consideration that it may have difficulties with the P and the P dagger, which they are not equal. But having this Q downstairs means the wave functions have to be zero in order to see this P, and this works out fine. Indeed, this has been solved. The eigenfunctions have been found to be x to the 3/2 by a certain polynomial and an explanation term. But the big thing is the eigenvalues. E sub n equal 2h all times n plus 1, where n is 0, 1, 2, and 3. And that's an equal spacing here with 2 and 1 here. This is the ground state. But in the full harmonic oscillator, that has the eigenvalues of h bar times this now is n plus 1/2. Indeed, this 2 situation and this 1/2 situation makes this like a brother to the full harmonic oscillator, and the situations have the same kind of things, having this equal spacing. I claim this is the answer to the question of the half harmonic oscillator, and this is incorrect physics. Now let's go to the next page. How mathematics may fail physics. Here's a function phi of x, and for which phi of 0 equals infinity. Here's our case, phi of x squared, 1 over magnitude x to the raised to the 2/3 power. And we're going to do an integration from between minus and 1 and plus 1, and the answer will be finite. That means this thing can be infinity within our integration, so we'll call that an integrable infinity. However, if we square this term and then have absolute x to the 4/3, our integrate will be infinity. Now the physics should be considered. Phi of x could represent nature. Nature's wonders do not reach infinity. Maybe this kind of math fails physics. Well, here's an expansion story for the common field theory. Here's the momentum term, the gradient term, the mass term, and the interaction term. The interaction term has nearby a power p and s for the number of spatial dimensions, but s plus 1 is the number of space-time dimensions. And we are interested in the integral of this Hamiltonian, and that must be finite. But this could be an integrable infinity. Perhaps here, but even here more dramatically. Set g equal to 0 and take a pi and a phi, all of them, and take any point in here for the different functions here. So all in here are those that have a finite integration up to this point. But if I turn on g and get a large p, for example, greater than or equal to 2n divided by n by -2, that gets infinities up here, and the little region in this middle is what's left over for finite values of the Hamiltonian. But if g goes to 0, that domain is not going to change. It's here, and that's a seed for a non-renormalizability. Here is the quantum Hamiltonian in canonical quantizations. We'll take the Schrödinger representation for these terms, and here is the momentum operator squared. And Monte Carlo studies for models of this kind for both P and field to the power 12 and 3 space-time dimensions, as well as power to the 4th and force-based measurements are unacceptable when you use canonical quantization. What does that mean? Well, suppose G was 0, and there would be some results from this particular story. Then you turn on G, and you find the same roads essentially are what you got. What are the results? So that's certainly unsatisfiable. On the other hand, being acceptable uses affine quantization, which means if Q changes, the results change just as well. Now, here's an example where mathematics can help physics. It's again an ABC story. We had phi up here next to pi, but now we're going to feature pi as the quotient of kappa divided by phi. Well, phi should not be 0 or infinity. That would not help kappa do anything here. So that magnitude should be here. Pi is will be the time derivative for phi. So that should be 0, and that can be kappa. That can be 0 here, but these two should not be infinity. And here we have the integration again, which is finite, but over here, and for power p, any positive power will have a finite integration because of this fact here. So there are no integrable infinities there. Phi of x can indeed represent nature. Nature's wonders do not reach infinity. Maybe this kind of help can math help? Yeah, physics. Yes is the answer. 2 beginning slides and the quantity. And here we have ingredients for an operator integration. Kappa dilation field, we'll call it, times pi and phi taken away from 0. Here is the operator, kappa. Here, dilation operator, which is self-adjoint, has a pi dagger and a phi and a phi and a pi all as operators. And here is still the 0 is missing. Here is a typical Hamiltonian in affine behavior. And that gets promoted to the classical function of kappa and phi, the quantum function of kappa and phi, and then the quantum function for the operators, kappa and phi here. That's all of AQ. And now at AQ, we are entering the gravity study. We have a dilation field here, I'll call it, of upper A and lower B, which is basically pi ABC and Q BC and summed on C, and Q should be positive, as we know. Here is the operators of this self-adjoint dilation operator, kappa, pi prime over phi and phi pi, and kappa G is 0. And for our Hamiltonian function, we'll take the Adam Arnold Misner story, and that is given by the wonderful processes of the coherent state to have the classical function of these variables equal to the quantum function of these variables. And that is taken over as the quantum function of these variables. And the pi in this slide level is the dilation pi. Now here is some ingredients for a path integration. We have canonical quantization, including H bar. And our fields go between minus and plus infinity, except we throw away 0 here for that. Here is our typical field, and we've added Hamiltonian, and with this is that we added our h bar term, h bar squared over phi a squared. And to make such path integrations proper, we need a Wiener measure. And here are the ingredients for the measure here, which will become part of the Wiener measure when we divide by t bar squared. And this is canonical story, which means it's Cartesian. And now for the gravity story here we have the ADM Hamiltonian here, and we want to make a Wiener measure. However, that would be complicated to put symbols here with ingredients on their side, and that's going to be very difficult. On the other hand, we can reuse this G A of B downstairs to dP AB quantity squared, and G of AB upstairs, and G of AB downstairs with a D in front and squared. This is to remind you that we have had a case before. Oh my God. Constant negative curvature, which I asked you to remember. Okay, so here is a little more story about the quantum field theory. Here's our basic variables, kappa and phi. Phi should not be 0, and all these should be finite. Here's our Hamiltonian density. That should be finite for all x, and it will be in this situation here because of the properties here. Here's the integration that takes that to the full Hamiltonian. And to summarize, we have found that phi squared should be positive, phi should not be 0, and phi should not be infinity. That means it's sandwiched between 0 and infinity at magnitude, and that raises to the power p, and therefore there's no more integral infinities coming from this term. And to quantize things, we use the Schrodinger representation and put kappa pi first on phi on kappa, phi on pi, with kappa self-adjoint, and our Hamiltonian for the affine quantization has kappa or surrounding phi to the -2 here and there, and here the rest is Schrodinger state. Now here we write a quantum field theory dealing with our exercise in which we promote affine quantization to the canonical quantization in H bar. Here is our Hamiltonian for the thing we're going to be considering. We have a coherent states here, and we have rules on the fiducial vector here. Here we have a time advancement between two covariant states, sorry. And that's going to look like this. We have our Hamiltonian term, which is all of this mess up here. And we have our H bar terms, as we were allowed to have the H squared divided by phi of x and t squared. And this is the Wiener measure that's here. It makes that a good path integral. And H bar squared has been used as 3 H bar squares earlier in the Monte Carlo stories, and that raising that has helped it a lot. Here is quantum gravity 2. We will take the little q greater than 0, e to the natural log of q that runs from plus to minus infinity. Here we have our matrix, diagonal matrix, G11, G22, G33, all of which should be positive. They can be raised to an e to an x, to a matrix upstairs, which we'll call eta 11, eta 22, eta 33. They're both diagonal. We can bring in the rotation of matrices from the SO3 to fix, spread this out and here as well there. And this gives us a story, which gives us the AB, and this comes from plus and minus. Here is the fiducial vector thing, and here is our coherent state with the eta family heading the dilation operator of the quantum. Here we have then the integration, path integration using the Laplace Lagrange Lagrange stuff. I'm sorry if I had a lot of that, or Lagrange parties. Anyway, here is the Hamiltonian extra term coming in, and we have our Hamiltonian. Hamiltonian is down here, using the ADM Hamiltonian and the Lagrange multipliers are there. And here we have our strange Wiener-like measure that captures the story. The Lagrange multipliers are getting, can be seen in details of the constraints in an archive situation. Summary, I give a big bravo to coherent states, affine quantization, and AB story. Canonical quantization has solved many problems. Affine quantization can solve many more problems. Correctly quantized the harmonic oscillator by canonical quantization. Affine quantization indeed correctly quantized the half harmonic oscillator. Affine quantization can tackle different problems. And here is Q equal to 0 is what we've been dealing with, but Q should be P, positive and or negative. And indeed, we could have these both together as a slicing the coordinate space in two terms. There's going to be a left, a middle, and a right. Throw away each side and keep the middle. That's a place to put in the problem of the particle in a box, which is still suffering under using only sines and cosines. It needs some tuning up. And the dilations are versatile in this story, and they're going to be used in here. Let quantum field theories and quantum graph seek valid results. Affine quantization is doing just that. I have a paper released by Archive. It's called How to Secure Valid Quantizations. And that was admitted by 5 days ago by our kind, and I hope you might look at it again. I've written a book that's entitled Enhanced Quantization, and chapters 9 and 10 are of interesting. Thank you very much.
Thank you for the nice talk. So we are about up against the coffee break, but we do have time. If there's an urgent question from the audience, please ask away. I'm afraid I'm not much of an expert on quantization myself. All right, well, I'm not seeing one in the room or on the chat. It may be that people are wanting to walk over and not miss the coffee. So thanks again for the talk, and we'll reconvene in half an hour.